Hello everyone, welcome back to Power System class again. This is lecture 16. In this lecture, we're going to talk about line compensation. What is line compensation means is that line could be fully loaded, lightly loaded, or no load, right? If you have line is fully loaded, your receiving end voltage tends to go down from the sending end voltage, like this line over here. Oops. Like this line over here, right? So if that happens, you need some kind of support for this line to bring the line voltage close to your rated voltage over here. And if it's no load connection like this one here is no load, then your voltage has to go up at the receiving end. Then you need some kind of support to bring it down to the rated voltage. That's the line compensation. So why is that? Inductive load, if you look at here, inductive load over here has a lagging power factor, so current is lagging. Then you add the line drop there, your Vs comes higher than your Vr, right? Same thing is showing over here, right? In capacitive load, your current lead the voltage. Then if you add line drop here, your Vs is basically smaller than your Vr, right? Okay, so that's what is showing on the no load condition over here. No load condition over here, your line becomes capacitive. In fully loaded, your line becomes inductive, right? So because of that, you need the compensation either way. Sometimes you need to bring the voltage down, sometimes you need to support the voltage up. So normally inductor is lagging, so is bring the voltage down. Capacitor, leading power factor, is bring the voltage up. So that's why I have two different kind of compensation here, shunt reactors, inductors to bring the voltage down. In heavy loaded transmission, we need shunt capacitor, static bar control, TCR, and all other method to bring the voltage up. So first the shunt reactor over here, so you have no load connected. That means your load over here is disconnected now. So if that is the condition over here, so your current becomes this, because you only have shunt inductor over there. Then if you modify this equation with that current, you get this value over here. So this is the shunt impedance. This is the shunt impedance of the reactor. It depends on few parameters. It depends on what is the ratio of Vs over Vr, right? And also depends on how long is the line is, right? So if I want this to be 1, that means I want my receiving end voltage as same as your sending end voltage, what I'm looking for here. So let's say this is the sending end, this is the receiving end here. So in this case, you're no load, so your receiving end voltage is going up. I have to bring it down. So that means I want that voltage to come down same as my sending end voltage. So this two voltages would be same. This is what your shunt reactor is doing, right? All right, so now this is the same equation here, so you can see the IS equation over here too. And if in the midpoint, or the midpoint voltage is also can see here, if X is L over 2. All right, one more thing here, for the uniform voltage profile, we don't do end-to-end compensation. We have inductor in regular interval of the transmission line. So your voltage profile should look like this for this one here. If this is the expected voltage, you should see like this. I mean, every interval you're trying to bring the voltage down until you receive at the receiving end, all right? For shunt compensation, in the opposite case, you want to heavily loaded, your voltage goes down, so you need the support to bring the voltage up. You need support to bring the voltage up. And how much voltage, how much reactive power you need to maintain a voltage at the receiving end is depend on this, right? And your B and A, those are your transmission line constant over here. So both are complex quantity, that the angle and magnitude. That's why you see that theta A, theta B over here, and delta is your load angle, right? So for example, you have a let me go back here. For example, you have a line that is over here. That line is supplying a load of 5,000 megawatt plus J 2,000 megawatt, right? This is the line supply. So this is heavily loaded, and this is your VR here. So because of the heavily loaded load supply, your VR is going down. So your VR is going down here. So you need to support the VR, right? This is the sending end over here. This is the transmission line. I'm going to do the transmission line here. This is the TL, and this is the sending end over here, right? So your voltage is going down on the receiving end because of the heavily loaded condition over here. You're trying to support the voltage up. So you need some kind of capacitor support here, right? So let's say it's transmission line A to neutral over here. You need some kind of capacitive support there. So how much capacitance you need to support the voltage at certain level, it depends on the reactive power. So for example, your reactive power equation I gave in the previous slide is that QR three phase is VS line to line, VR line to line over B cosine theta B minus delta, and another part over here. So I can so I know the sending end voltage, I know what I want at the receiving end voltage, and I know the B parameter and delta. So using this equation over here, I can see how much I need to support my voltage at receiving end at certain value. For example, I want to support the voltage at VR line to line. I want 480 kilovolts. So if I want that, if it will be line to neutral now, would be 480 over square root of 3 kV. That will give you 277 kV, right? So that's my line to neutral voltage at the end, what I want at the end, right? To do that, to the calculation, for example, this calculation now, this over here, comes to, so let's that now, so QR three phase now came down to 100 megawatt. This is not exact calculation, I just took the value. So now you need 1000 megawatt of reactive power at the receiving end to maintain the voltage at line to line 480 kV. But you have, if you look back here, you are consuming 2000 megawatt. So now, sorry, it's megawatt, sorry about that. It's megawatt. So now you need to take 1000 megawatt out of the load. How do you do that? It's inductive load. Now you need a capacitor there to supply 1000 megawatt to support it, right? So that means you need this capacitor over here, So supply 1000 megawatt. Then it doesn't have to come from the transmission line, right? So that's how you support the voltage. That means so now to do that, we can do line to neutral capacitor connection. What I'm talking about here, you can go if 3 line over here, in neutral over here. So A, B, C, you can connect capacitor line to neutral. All right, or you can connect them line to line. If you don't have a neutral, you can connect them line to line. Right? So either way, you need to know the voltage across the capacitor, right? To find the capacitor value, because you know this one right now, okay? So now, to find the capacitor value, let's do the line to neutral here. If you do line to neutral, I need the line to neutral voltage. So VAN would be 277 kilovolts, right? And Q is V squared by XC. My Q is here. I need 1000 megabar, but I have 2000 megabar, so I have to take 1000 megabar out of here using a capacitor. So the capacitor should supply 1000 megabar. So QC over here should be whatever I have, 2000 minus whatever I need, that is 1000 megabar should come from the capacitor, right? So to do that over here, so I know QC now, I know V, which is 277, I can easily find XC. XC would be V squared over QC. If I put the values back there, that should come like 277 squared, 277 squared over, okay, for the per phase, for the per phase here, it would be 1/3 of this. So per phase is 1/3 of that. That would be 333.33. So I have 230 ohm, right? Then I also know that your XC is 1 over the magnitude omega C. Then from there I can find the C. So that C will go from the line to neutral. If I put the capacitor line to line, then I have to use the voltage. This, my voltage over here would be 480, not the what do you call it, 277. So that only thing change over here if I do line to line. All right. So that's how you do. You use this equation to find how much reactive power you need to maintain the voltage at certain level in the receiving end. All right. So with that, then another, this is the right here. That's what we're talking about. Then you find the capacitor and put it there. Then for the series compensation, line is mainly inductive. So if you add a series capacitor, you take the inductive impedance out, and your line impedance would be smaller. What does it do? If you have a smaller line impedance, you have more capacity to transmit power, because you're taking the denominator smaller, so your three-phase power transfer would be higher. And that you can do that from 25 to 70% compensation in there. By doing that, make sure that you are not also, you make sure they're not introducing synchronous resonance frequency into the system. So now you have transmission line over here. With the compensation, it brings, this is the transmission line over here, right? Then your compensation, series compensation over here, and your shunt reactor over here. All right. Then your capacitor compensation could be added to this one over here, or it could be right here, your capacitor compensation. All right. So that's your compensation line. Compensation is done to support the voltage in the line because of like no loaded, light loaded condition or fully loaded condition. We're going to stop here for today for this part. Then we're going to see you for the next part.